Okay, good morning, everybody. Let me start right on time. Somebody will be late anyways. My name is Ralf Westphal. I'm from Germany, and I'm here to entertain you with a peculiar view of object orientation. But first, let me note that it's quite astounding to me that so many people actually want to sit in the front row here. Because you know the usual speaker habit is to pick someone from the front row and let them perform something on stage. Like, you sir, do you want to do a little software design for us here using the OOID method? No. Okay, no. Don't be afraid, I won't do that today. But I want to ask a question up front. What's for you the most important aspect of object orientation? How would you describe it in a bullet point list of attributes? What's object orientation to you? Anybody? Just fire out the words. Encapsulation. Encapsulation, great.
Maintainability.
Maintainability, great. Reusability. Pardon? Reusability. Okay, right on. Something else? Nothing? Oh. Come on. Huh?
Inheritance.
Inheritance, right. And finally, responsibilities, like single responsibilities of objects, classes. Okay.
Structured approach.
Structured approach. I thought we did that in the 80s. But then, okay, yes. And finally, come on. Yes. Okay. That's it? Cool, very cool. So let me introduce this gentleman to you. You know who that is? Anybody seen him before? No, he's not at the conference. That's Alan Kay. That's actually the guy who invented object orientation. He did that like in the 70s, I guess. And see, that's what he thought was object orientation was to him. Objects being things like biological cells communicating using messages. So did he use the term inheritance? No. Did he use the term polymorphism? No. Encapsulation? Maybe that's hidden behind using messages. Did he use the term reuse? No. Maybe that was of concern to him, but he didn't say so. That's object orientation. Okay, that's what this guy said at least. And now look at the usual definition of object orientation. Let's like Wikipedia page. And you see it's object-oriented programming, and it lists a couple of attributes here. Like, oh, there's classes and instances and abstraction and polymorphism and encapsulation, see there. Whatever. Cool, inheritance, it's all there. And where's messaging? Is messaging there too? It is, indeed, just one of like 10 bullet points. It says message passing. So the next question is, do you know what message passing is? If it's so important, if it's at the root of object orientation, if it's the foundation of object orientation, the most important term of object orientation, because that's what the father of object orientation said. So what does message passing mean? Do you do that in your daily object-oriented practice, message passing? Do you let objects communicate using messages? Who's doing that? Okay, that's not even 10%. And may I ask you what your definition of message passing is?
So I'd say we use two definitions. So we use MSNQ as a messaging system to communicate between different systems. And we also use an event-based model within an application to notify parts of the application that things have happened.
Okay, thank you. Very interesting. I asked him for the definition of message passing, and he named a couple of technologies. Is that the definition of message passing? Not really. So what's the definition of message passing? Let's turn to Wikipedia again, and it says something like message passing is a way of invoking behavior through some intermediary service or infrastructure. MSNQ. Right, that's an intermediate service or infrastructure. Rather than directly invoking a process, subroutine, or function. So there's some indirection, it seems, necessary for message passing, at least to this, according to this definition. By name as in conventional program, and so on, so on, so on. So the regular method call on an object is not message passing, according to this definition at least. So where's message passing in our daily routine of object-oriented programming? I'd say it's absent. This is deplorable. Alan Kay says, wow, messaging is the big idea, and it's missing. This is the big idea's messaging is his answer to a question by some interviewer who asked him what's lacking in today's object-oriented programming. So it's missing. I think this could be at least one of the reasons why our object-oriented programs look like they look. They are hard to maintain, it's brownfields, it's heaps of legacy code. You have a hard time to change whenever there are new requirements. Okay, so what can we do? What is messaging? Let's go back to Alan Kay's original idea. See, that's two biological cells. That's a nerve cell and that's a muscle cell. And he had in mind that objects would communicate like biological cells using messages. So where's the message in this picture? It's here. It's the acetylcholine flowing from this nerve cell to the muscle cell. So whenever the nerve cell is like working, it's outputting acetylcholine. This acetylcholine jumps over this gap here, synaptic gap, I guess, to the muscle cell and then makes the muscle cell working. So my question here now is, if object orientation is like those cells communicating, and we are doing object orientation today, then where is there dependency injection in this picture? Because it seems a foundation to today's object-oriented practice. Wherever there are two objects, we're thinking about making them dependent in some way, and then making them not dependent on the actual implementations, but on abstractions, and then the actual implementations get injected at runtime into the caller. Okay, so where's dependency injection in this picture here? Strange, right? It's not there. Or look at this. It's like on the higher level. It's organs. So those organs are working together, of course. Where's the dependency injection there? I only see blood flowing. And then something happens with the blood within the lungs. There's an oxygen CO2 exchange. So where's the dependency injection? I don't see it. Where's the dependence on abstractions instead of concrete services? So who is servicing whom here? Who is servicing whom here? Or, final picture here, since I'm from Germany and we invented this. No, just kidding. Where's the dependency injection here? Where's the inversion of control here? Or is this more like cells? Is this more like message passing? I'd say so. See, for me, message passing, let's go back to the cells here. Message passing means, okay, there's a message. Haha, of course. The acetylcholine. And the guys who are like working on this message, one is the producer here, this nerve cell, and one is the consumer, the muscle cell in this picture. Those guys don't know each other. That's the point. Message passing is about two parties agreeing on a message contract, yes, on some kind of messages they understand and they can produce, but those parties don't know each other. That's the same here. That's the same here. And so I come to my first principle of messaging. That's the principle of mutual oblivion. Messaging is when there's a one-way data transport, so like the acetylcholine moving from the nerve cell to the muscle cell, a one-way data transport between mutually oblivious functional units. See, I don't want to say function, I don't want to say class or object, but I'm using a more neutral term here. So that's messaging. That's deviating from what Wikipedia is saying, where messaging is only if there's an intermediary in place. Well, maybe we can say that like this gap between the two cells, there's an intermediary who's carrying the message. Yeah, maybe. But then I don't find that so important. I find it more important to say it's a one-way communication. Messaging is one-way communication between two parties who don't know each other. One is just producing some message or data, and one is consuming this message, the data. That's it. So how then can we as living beings, or any living being, or even a cockroach, how can we like live at all if it's just one-way communication? See, we are thinking of software, even very, very complicated software, maybe even complex software. We're thinking of software as like being constituted of those client-service relationships, right? So where's the client-service relationship within your body, within a cockroach? There's no client-service relationships. And still those living beings live. They're so much more complicated than our software, but still it's working. How can that be without client services relationships? How can that be with just messaging? Because it's about proximity. Because this one producing acetylcholine and this one accepting acetylcholine, because they're close to each other, they can function as a whole that's different from the parts. So there's the sum that's larger, the whole that's larger than the sum of the parts, or the bigger than the sum of the parts. So there's something else that's making them to be close to each other. That's the wonder of life. That something makes all our cells be so close to each other in a good way so that the whole comes to life. That's what we need to get done for software, I guess, if we want to do object-oriented programming, according to Alan Kay at least. Maybe you're more of the, I don't know, Grady Booch fan or something, then you don't want to do that. But if you want to stay true to the father of object orientation, you should think about how you can do messaging in your programs. Okay, so let me first abstract the biological picture here. We have to get a notation. How could we depict messaging in our programs or for our programs? How can we design systems that use messaging? I mean, I'm not inventing this here. There are already notations out there, but they are maybe not as well known as UML class diagrams. And in addition, of course, I guess, if you're like the German crowd, there's not more than 10% of you using UML at all. Okay, so how can we depict this relationship between those mutually oblivious parties who are working together using messaging? Let me abstract here the producer with this ellipse or circle or whatever, and the consumer with a like ellipse or circle or whatever. And the message flow between the two is an arrow. I'm using an arrow just for message flows. I'm not using an arrow for dependencies. You'll see another symbol for dependencies in a minute. That's what I don't like about the UML. UML is using arrows all over the place, and you first have to think, well, what's the meaning today? What's today's meaning of an arrow? Sometimes it's dependencies, sometimes it's something that's flowing. Okay, to me an arrow is just data flow. And this here within brackets means that's the data that's flowing there. It's an acetylcholine data type, so to speak. Okay, nerve cell is issuing data. The data flows across the gap and then, or along the arrow, and then hits the muscle cell, and the muscle cell, well, does something with the data. This is data flow. It's a data flow diagram. So messaging is about data flow. It's not about control flow. Control flow would mean, you know those flow charts or structograms, I don't know. Control flow would mean, okay, if this is finished, then control flows to that, and there's no more control, and the control sits here. That's not the case with data flow. Data flow, well, data flows out here and in here, and it doesn't say anything about control. Maybe control stays here too. Maybe more data is produced while data gets consumed here. Maybe, maybe not. So data flow is oblivious to where the control sits. Control can be in many places, but it doesn't need to. So don't think of data flow diagrams as diagrams for parallel processing. I don't want to make it hard on you. Switching from your current view of object orientation and synchronous processing should be not like a leap. I don't want to make you leap. I just want to make you take a step, a small step. Don't try to do this in an asynchronous way just tomorrow when you're back at your office. It's synchronous programming, yes, and control might flow with the data from here to there, but it doesn't need to. But for the moment, let's assume it does. Okay, so how do we then, if this is like an object-oriented diagram with messaging in it, how then do we translate that into our current programming languages? That should be an easy translation, right? Like you take a class diagram and you know right away how to translate that into like C# code or Java code or Ruby code, whatever. So how do we translate that? It's very easy. There are several translations. See, it's one of those functional units. There's input flowing in, output flowing out. And the most simple translation of that is a function. So some responsibility takes in a T input type and produces data of T output type. That's message passing style programming. So in fact, those guys who said, well, calling a method on some object is in fact message passing, they weren't that wrong. Yes, it can be message passing. We'll see in which cases it's message passing and in which cases it's not. So, but the form, this form of a function, it's not bad. That's good. It's message passing, or it can be message passing. That's the simplest translation. There's one input, one output. You translate that to a function, it's all well and fine. But there's more translations because, for example, how should this function look if there's not just one output, but several outputs? Like there's an integer going in, maybe a number saying how many numbers need to be generated. You pass in 10, and then 10 numbers should be generated, like 1, 2, 3, 4, and so on. How do you depict that? You could say, well, it's T output could be a list of those numbers. Yes, okay. But then maybe a folder path gets passed in. And the output is supposed to be file names. All the names of files within this directory structure. Maybe that's 10,000. Maybe it's 100,000. I don't know. You want to wait for them all to be enumerated and compiled and then passed on as a list? No, you want to pass on each file as you encounter it during traversing the directory tree. So then you need to have a function with several or output at several times. How do you do that? You can't. That's why you can translate this functional unit to a method or a subroutine or procedure like this, where the input is T input and the output is passed on using a continuation. You know continuation passing style programming? Who knows that? Okay, just a few. See, this is where delegates and lambda expressions come into play. You're passing in a delegate here, and this delegate is called every time a new output got generated. There are a couple of free places in the first row here. See, I'm going to call him up. So in case some responsibility is not just producing one output item, but several, and in a manner so we don't really know when they get produced, we don't want some responsibility to be just a regular function with one return value, but rather we want this to be a subroutine calling an event handler. This is nothing more than an event, but it's not an event like the event field of a class. It's a continuation. It's just one function pointer passed in here. Okay, then there's a final translation. Some responsibility becomes a whole class of its own. I'm not recommending this. You shouldn't do this like all the time, but sometimes it's the right way to translate some responsibility with a generic name for the processing subroutine, and then an actual event here for the outputs. Sometimes that's the right way to translate it, sometimes it's not. We'll see different translations. Okay, so as you see, if you draw a message passing diagram, it's not hard to translate those functional units into code. And that's very important to me because people come along when I show them those bubble diagrams and say, oh, well, bubbles don't crash. That's true, so we need to make sure we know how to translate those bubbles into code. And it's very, very clear. Let's start with those data flow diagrams. So we want to have more than just one of those bubbles. That's a one-dimensional data flow diagram. It's one-dimensional because it's like just a line. Just a line of, or a sequential process of those functional units. Some x is the input of A produces from this x some string, and B produces from this string some stats, and C consumes those stats, maybe stores them in a database or outputs them on screen, whatever. Let me direct your attention to small differences here. This x is in small letters because it denotes some value, the name of the value. See, the string compared to that is a type name, a standard type name. So if it's clear to you what's flowing from A to B, you don't have to give it a name, you just tell, well, this is the type of the data. Sometimes it's obvious what's flowing between two of those functional units. And then finally, here, what's flowing from B to C is denoted by a type name. I'm using capital letters here. If the first letter is a capital letter, then to me at least it's denoting a name of a type of data that's flowing here. And writing stats in small letters would suggest it's a simple type, but writing stats with a capital letter means, okay, I have to think about how this structure actually looks and write that on the side maybe somewhere. Okay, that's simple. How would we translate this into code? You remember? Function with continuation, class. So let me show a couple of translations. This is one translation, obviously, right? It's just functions. Functions called one after the other. Calling function A produces S for string. Then B called with S produces the stats, and then C is passed in the stats. That's easy, okay? This looks like a bit difficult, right? It's at least not difficult, but unusual. This is the continuation passing style translation. We're calling A using X. And then also at the same time, a continuation, a lambda expression gets passed in. This is a lambda expression. And the lambda expression says call B using S, where S is what gets output by A. And at the same time, we're passing in C because when processing S, call C whenever necessary. This is unusual, I know. You have to wrap your head around that. Takes some time. Takes getting used to that. But I assure you, you do that like for 4 years and you don't want to write it anywhere else. This is an completely equal translation to that one up there, but it provides you with some more degree of freedom, right? Up there, there's only one return value per function. Here, we can encode, well, B gets called like 10 times, C gets called like 20 times. Why not? It's just events getting fired by those methods. Speaking of events, this is another translation. Here I translated every functional unit into its own class. And now I'm connecting the event handler here to the event there. And then the event of this one here, I'm connecting to the event handler here. And finally, I'm starting the first functional unit and say, okay, process X. And then it fires on S, B processes the S values and produces stat values and fires them, and C processes those stat values. That's another translation. And the final translation, which is not C#, that's all C#. This one here is F#. There's this pipe operator. It's again all functions, but now they are concatenated using the pipe operator, and it's looking much, much simpler. So maybe this is one piece of motivation for you to have a look at F# at some time. Now, you have a hard time reading this. Maybe not the top examples, but then the other ones. But let me assure you, reading them is quite easy. It's always top to bottom, or left to right. Even here, it's left, right, top to bottom. That's a natural reading order. That's completely the other way around compared to what we're doing now, today. Because today we're used to nesting. And nesting is calling functions within other functions, and not within other functions, but when calling one function, we first have to call another function. So we read it from right to left, from inner to outer. That's what we got trained. Years and years of training in our head. We can read that, yes, but still it's more difficult. I could have written the upper example like that. I would have written C, open parentheses, B, open parentheses, A, open parentheses, X. I could have written it like that, but I don't, because it's hard to read. I would have to read it from right to left, from inner to outer. But this is easy to read. And that I find very important. Make your code easy to read, easy to understand. Okay, but that's still simple flows, one-dimensional flows. Now turning up the heat a little bit. This is two-dimensional flows. As you can see, two-dimensional flows means not just one dimension, but 2 dimensions. And this second dimension comes into play when there are functional units with more than one output or more than one input. Again, the question is, how do you translate that? Well, it's the same as before. We can use, for example, continuation passing style. We are calling the M functional unit with an F, and this one goes out and has 2 outputs, one this direction and one in this direction. Let me go back to the picture. M with 2 outputs. See, M with 1 output, 2 output. This is the output, the empty output, so to speak. See, that's, this one here. That's the other output. And then we are continuing this this gain, we're calling the next functional unit with this parameter, and there's another continuation here. That's the class up there, so I'm mixing two translations here. Continuation passing style and the other one that's called event-based components, which is a bad name, by the way, but still it's called like that because it has those events for the outputs. I'm mixing those two translations. Here we're calling the O class with two different methods for the inputs. See, that's the O class. One method to process this data and one input method to process that data. Another look at the data flowing here. We know already this. Okay, this denotes some f value. This denotes no data flowing, just like a signal. This string star means it's a list, some kind of list, because this is just a design. I'm staying abstract here. I'm not saying this is an array, this is an iList, this is whatever. I'm just saying, well, more than one value, and I can concretize that during implementation, if I like. I could also write down here like those angle brackets and say it's an array. This denotes the value including a type. If you want to make it crystal clear what's flowing there, we can do it like this. And this here, that's interesting. This says, okay, it's a G flowing there, but see the star is outside the parentheses. This means it's a stream. That for each signal coming in here, it's not just one value, it's probably more than one value. Maybe 0, but probably more. So it's one signal and one value flowing out there, another value flowing out there, another value flowing out there. That's a stream. That's a notation for this example where I said, okay, a path name gets passed in, and then maybe several file names flowing out. I'd write like this. And obviously, we have to translate that using continuations or events. That's what I did here. Passing in the continuation. Okay. Next step. It's 3D flows, three-dimensional flows. One dimension, just a sequential line of processes. Two-dimensional, it's sometimes parallel processing. You could do that. If the data is okay with this, we can do that actually by doing parallel processing. Why not? But we could also do this by parallel processing, running m at the same time as n. This diagram is not clear about that, and that's okay. It's a design. We have to think about that, but we don't want to be bogged down by such detail at this moment. It's just a design. And this third dimension means there is a flow, but this flow is like a detail view, a refinement of a larger encompassing flow. See this one containing all the other functional units? It's looking like this. That's just a different depiction of the same thing. There's X flowing into integration, whatever that means. And then if I zoom in, if I open up integration, I see, oh, in fact, integration means A, then B, then C. That's the actual processing pipeline. But that's too much detail for me most of the time, so I'm pulling this all together and creating a new whole from the parts, and I call that integration. So whichever way you go, that's okay. If you start out with this one, the sequential flow, and then think, maybe this is like, I can find this one term describing those 3 steps. That's just fine. You go bottom up and you create the upper functional unit, the integration unit afterwards. Or you do it the other way around. You start with the upper functional unit. You say, I guess processing the data means doing integration whatever. And then later on you say, oh, now I know more about this problem, and I know we have to tackle it with actually 3 separate steps. Top down, bottom up, that's okay. Or do the yo-yo programming, top down, bottom up, top down. And now here comes a very important principle into play. Once we start with those 3D flows, it's all messaging, all data flow. One thing we have to keep in mind to make this different from functional decomposition of the 80s. I call this the integration operation segregation principle, IOSP for short. And that means once 3D flows appear, we want to be very careful what to put on those different levels. What we want to do is keep our responsibilities straight. We keep our responsibilities focused. So this here focuses for the integration on the responsibility of just integrating code. What they do down here, I don't care. It's like all the logic you want. What is logic? Logic is expressions, control structures, and API calls. That's what is our software about. If our software is very small, we just write down a couple of expressions, a couple of ifs and whiles and select and case statements or whatever, and that's it. No subroutine if our software is very small. And that was the case in like the 50s. It was just small software, a couple of lines of assembler code, and that's it. There were no subroutines. But then, once software got bigger, subroutines were invented. Not just jumps, but calls with a return address. But calls are not logic. Logic, that's what our software is for, is just expressions and jumps. Expressions and jumps, and calling some API. That's what I want those low-level functional units to focus on. That's our workhorses. That's where actually the work is done of our software. And all levels above that have a different responsibility. And I assume your code base looks different. In your code base, you have those hierarchies, yes, but in your code base, logic, expressions, if statements, API calls happen on all levels of this hierarchy. Logic is smeared all over the place, and that makes it hard to maintain. And that's different here. Logic is confined to the lowest level of such hierarchies, and all upper levels are just integration. There's no if statement in integration. There's no expression in integration. There's no API call in integration. And that's a hard and fast rule. That's easy to observe in code. You look at a method, and this method calls another method. Okay, it's integrating by definition. If one method calls another method, it obviously doesn't do just something itself, but it also delegates something to somebody else. Okay, so it's two responsibilities right away. That's not single responsibility. So what you do is you pull out all the logic stuff to a lower level, and then you have just an integration method. This is how this looks with a couple of levels. See, up there is one-dimensional flow. Then the central functional unit gets split up into two functional units. Both of them get again split up in further functional units. And so that means logic just resides here and here and here and here. And of course, up there in the left and the right functional unit, because they are also at the bottom of this dependency tree. Dependencies, unfortunately, won't go away. Or put the other way around, dependencies are great to tackle complicated problems. So we can divide and conquer. But we have to diffuse dependencies. Dependencies work like bridges for change. Wherever there's a dependency, changing one side of the dependency endangers the other side of maybe to be changed too. That's what we want to avoid, right? We want to confine changes to the place where they're happening and not get them rippled down or along all those dependencies to other places. In order to do that, we have to be very, very careful who is dependent on what. And by doing it like this, by focusing the responsibilities up here on just integration, we are taking those upper functional units out of the way of changes down here, because this functionality here, is not dependent on this one and this one, not on the contents, but just on their presence. It doesn't work on the data flowing between the two. It just sees to that those two are put next to each other. This one is like the forces pulling a nerve cell and a muscle cell together into each other's vicinity. That's the only reason for this to exist, to put other functional units close to each other. So, when you read this, see those dependencies, and the upper two ones don't have any dependencies, so they are operations by definition. The other ones here I open up, they are integrations, and those down here are operations. And you do that as far as you want to go. You refine your functionality as far as you want to do it, as far as you see how this could benefit you, and then you stop. Then you stop at this tree here. And now you know, okay, when I implement this and that and that and above this, then I have to focus on just integration code. That means calling functions, nothing more. And when I implement this, I can do whatever I like. Except for when you start maybe implementing this here. Well, the session is over, the team spreads, you have the responsibility of implementing this, and you find out, this is more complicated than I first thought. Then you do the same as before. Within this leaf node of the dependency hierarchy, you can continue as before. If you find out this is more complicated than first thought, you can say, okay, maybe I need more steps. Maybe I need more individual steps to actually solve this orange problem here. And then you can nest within this orange functional unit a hierarchy like before. So software structure actually is recursive. It consists of trees divided into integration and operation. And operations by themselves can also be trees of integration separated from operation. Integration hierarchies or levels, there are many of them, that's okay, but there's only one level of functional operations. And you might be wondering, when is going to get to classes? Huh? We are doing object-oriented programming here, and when are the classes coming along? Wait a minute. Okay, first I want to tell you, this is in compliance with Abelson and Sussman, who wrote this famous book, whose title I keep forgetting. Can you read it now? It's like a Principles of Structured Programming, Software Programming, something like that. And they are speaking of something they call stratified design. That's what they recommend. That's in fact what Alan Kay also recommends, stratified design, not layered design. What's the problem with layered design is when you compare it to the OSI 7-layer structure, You know the layered architecture, right? Presentation layer, business logic layer, and data access layer. Great. And then people compare that to the OSI layers. Is that okay? No, that's not okay. That's not okay because OSI layers are different. If you look at the OSI layers, they actually describe abstractions. The lowest level is doing something in high detail. Then the next layer above that is doing the same, but in less detail. Then the next layer above that is doing the same in even less detail, and so on. So they are truly abstracting. Each layer is an abstraction of the lower level layer. Great. They are all about communication, right? Very low level communication, top level communication, maybe objects communicating with each other. And lower level is, I don't know, UDP communication something, then TCP, blah, blah, blah. Okay, so it's all abstractions. Each layer is above another layer is more abstract than the lower layer. And now think about the layered architecture. So business logic is an abstraction of data access? I don't think so. And presentation logic is an abstraction of business logic? No, of course not. Each layer is doing something completely different. OSI layers, abstraction, all the same. The architectural layers, all different. So what Abels and Sussman are talking about is not the architectural layers. They are talking about something they are calling stratas, or it's stratified design, where each layer provides a whole view of a solution, but at different levels of abstraction. Okay, and they talk about DSLs, the special languages to actually formulate the solution to problems. And then you could think, well, do I need to design my own language? Oh, how do I do that? Is that an embedded DSL or a standalone DSL? And what's my meta-programming environment for that? And so on. No, you don't do that. You don't need to take up that measures. What you do is you just do messaging. Messaging according to the IOSP principle, because this defines a low-level language of what's supposed to happen. This is a little higher level language of what's supposed to happen, because all of them are replacements for the top layer. The top layer says, I want to get it all right now. Pass in some data and get the job done. One functional unit. Then on the next layer it says, okay. Getting the job done, getting everything done means step A, B, C. On the next layer it means, okay, getting the job done means A, B, or X, Y, and so on. So each level describes like a vocabulary for the whole problem, but on different levels of abstraction. So that's why I call this stratified design. I find it in accordance with Abel and Sussman, and that makes me sleep well at night. And now here, finally, to your relief, it's classes. So far I've talked about like functional units, very abstract way, and you saw a translation of those functional units into functions, some way or the other. But we have to find, of course, places for those functions to live in our programs within classes. So what we do is, in the end, we look at all those functions, at this hierarchy of functions communicating with messages, and ask ourselves, well, do we see patterns? Are there any patterns? And if there are patterns, we can draw together functional units into classes. Maybe a couple of functional units, let me go back here. Maybe some of those functional units, maybe those two here, share some state. Okay, they could go together into one class. Or those functional units over here, they share some API. Maybe they're all accessing a database. Or maybe this functional unit here is a very certain responsibility within the domain. Maybe this is doing the formatting, whereas this is doing the data access, and this is doing something else. Okay, so it's mostly very formal criteria allowing us to find similarities between those functional units and split them up or join them together into classes. That's cohesion. Accessing the same state, that's cohesion. Accessing using the same API, that's cohesion. Or here, what's the similarity here? It's integration. It's all integration functional units. So why not keep them together? So what this leads to is, interestingly, a class diagram like this. There's a number of operational classes. They just contain operations. Interesting, isn't it? The functional units, the functions, are independent of each other. There's no dependency horizontally between those functions doing the stuff, containing logic. And there's no dependencies between those classes containing those functions. That makes them easy to test. Very easy to test. But there are dependencies, see above. The integration classes depend on other integration classes or on operations. Yes, but interestingly, integration is so simple. You hardly have to test it at all. It's like 5 lines of code calling method A, B, C, D, E, and that's it. How much do you want to test that? I mean, can't you read the data, process the data, write the data? How difficult can that be? How much can you get wrong? Okay, if you want to test it, well, test it, but you don't have to. So testing all those levels of integration is hardly necessary. It's easy. You review them, that's great, but you don't have to put intricate tests on them all the time. Of course, you want to have an acceptance test or an integration test right on top, sure, but you don't need to test all those levels all the time, at all times. What you want to test sufficiently, comprehensively, is operations, but that's easy to test. Those are hard to test because they have dependencies, but then you don't have to test them. They are easy to test, and you have to test them, and there's difficult stuff in there. Great. And finally, there's another level here. That's just data. And data is, again, easy to test, because data, and now brace yourself, doesn't contain any functionality. I know, this is hard to believe, very hard to believe. But I'll tell you in a minute why I think that it's necessary. So what this is, I think, is pretty solid. It's according to the solid principles. There's single responsibilities, and not just like content-wise. It's formally single responsibilities. Just the data responsibility, just the operation function responsibility, just the integration responsibility. And within the operation responsibility, of course, we have like data access responsibility and formatting and security and whatnot. Is this open-close, O for the open-close principle? Is this easy to change? Is this open for extension and closed for change? I guess so. Let me just quickly go back here. Because what you can do is, whenever you need to add some feature to such a functional hierarchy, message passing hierarchy, what you do is you don't change this bubble here. Instead, you thread in a new bubble between the two. That means you change this one here, yes, but that's so easy. It's just another line of code. How difficult can that be? You don't need to like do strategy injection, stuff like that. That's okay, you can do that, but you don't need to. It's just simply leaving this alone, leaving that alone, and putting another functional unit between the two. Or in parallel, whatever. So yes, I guess this is open. Liskov substitution principle, Well, does it apply here? There's no inheritance in play. If you like, do inheritance. I hardly remember when I last derived a class from another class, but then do it if you like. What is this interface segregation principle? Oh, well, interestingly, the interface segregation principle is good and well. You know this example from Bob Martin. There's like a modem or communication class, and it has an open, close, and read-write methods. And then he takes it apart and says, okay, you might have this one class, but then maybe you want to have two interfaces. One is for the established communication functions, open, close, maybe the iConnection interface, and the other one is for the read-write operations, maybe the data access, iData access interface. That's interface segregation. Great. But then, do I want to draw this now? Let me see. If this is a client, okay, now it's client and server, right? This is a client, and this client depends on some server. And the server has two functions, F and G. The single responsibility principle says that there should be only one reason to change, right? So what's reasons for C to change? What's reasons for S to change? Reasons for C to change should be, well, the task of C changes, right? That means single responsibility. If C is doing some calculation stuff, once the calculation, like the formula changes, we need to change C. Cool. But then there is another reason for change. What other reasons for change could there be? Well, if F delivers data in a different way than before, we need to adapt C. Yeah, what can you do? This is how it is when you are depending on some service. Okay, never mind. Is that all? No, there's still another reason. C is not just depending on S. It's not just it's not just a service dependency. There's another dependency. What happens if someone says, okay, I see S is too big. I want to split it into S, tick, and T. And this one is implementing F, and that one is implementing G. Does C have to change? Sure it has. Well, damn. Why? Nothing changed in the task of C. Nothing changed in how those services are delivered. But still, C needs to change. C now is depending on two functional units, on two other classes. That's what I call topological dependency. And topological dependency, meaning you're not only depending on a service, but also where the service is delivered. First, it's delivered on S, then it's delivered by S tick and T. So you're depending on where in the topological, on the topology around you, in the space around you, services are located. This is a dependency that's all over the place. All over the place in your code. And that makes it hard to rip code apart. See? It's nice and well to have the interface segregation principle, but then, you have to change all the clients. Once you have two interfaces, you have to change them. So I would say we should look at this. And here, there is no service dependencies at all. Interesting. So we are not suffering from this problem here. that makes it very well living by the ISP here. And dependency injection or dependency inversion principle, if you like, just fine. There are dependency hierarchies here. If you want to abstract the integration over there with an interface, just do it and do some dependency injection later on. All that's fine. To make it a bit more abstract here, so what we have is in the middle of it, it's heavyweight operations which are independent of each other. Great. And it's lightweight data down here. That doesn't mean there's no functionality on this data, but I would confine it to certain functionality. And this functionality is, well, seeing to that the data is consistent. If you look at the DDD literature, domain-driven design, you look at a much praised book, one of the first books written about that, and you look at the example, there's a customer class, and the customer class provides a method like check credit limit or something like that. Well, I'd thank my bank a lot if they would ask whether my credit limit was reached. I'd always answer no. So you should do that in your code. Have a customer class answer the question, is credit limit reached? No, I don't think so. That's much too much functionality, domain on this data class. If there's a customer class containing customer data, well, then the responsibility is to keep that data consistent. Great. Like a stack or a queue is doing a lot of work to keep data consistent according to some access pattern, FIFO, LIFO, whatever. And so that's what the lean data down here is about, because once it's lean, once there's only data structure and only some functionality on it, the chance of changes rippling from here through there up to there is limited, at least much smaller than before. And the other way around. If there are changes up here in this heavyweight functionality, chances of rippling down to the data is slim. And the other way around too. If our integration is very slim, like a dependency injection container is slim with regard to the domain, so there's hardly any changes that could affect the integration up there. So to keep our hierarchies, functional hierarchies or class hierarchies stable, to keep them easy to maintain, I suggest that we actually separate those fundamental concerns. It's data from operations from integration. Very, very formal separation. And now let me move to a small demo where I refactor some code. The code is doing some formatting of CSV data. The CSV data is coming in like this. So the semicolon is the separator, the delimiter. There's like a header line and some data lines down here. And I just want to transform this data into a nice looking ASCII table like this. Okay? It was pretty easy to do, right? You can do this as a code kata at home with your team. It's a bit larger than the FizzBuzz or Word Wrap Kata. That's what I want to do, and what I brought with me is some brownfield code, which already does it. Okay, so here's the brownfield. Should I enlarge this? Can you read it in the back? Yep. So this is brownfield. I don't want to go through every line here. It's one method doing some heavy stuff. Then there's this convert line to records field method. And there's another method down here. See, another convert to line. Why are there two of those methods? Interesting. And there's a final method down here. Create display line for record. There's a little typo in there. Okay, but this does the job. Oops. As you can see, there's an acceptance test here. I can run. And it's green. And it should show. Oh, no, not at this level. I thought it showed the output. Okay, so this is working, but it's not looking very nice, right? This is not really message passing style. It's something. But then I worked on that, and I refactored it to IOSP. Remember? Separation of integration operation. How does it look now? Ah, interesting. So the format now becomes very, very readable. It says, first parse the CSV data, then for each of those records, calculate the column widths, because that's an important point. If you remember, those columns here over here were as wide as the longest entry in those columns. So calculate the column width and then build the table. What does building the table mean? I don't know. Maybe I'm content by knowing this is the basic flow of operation for format. But if I want to know, I drill down. I drill down, and here I see, building the table means formatting the header. Then there's this underline line, just dashes and pluses. Then format the body. That's 3 parts of a table, like with HTML. And then assemble from those 3 parts the table. Easy to read. If I want to know more details, I can drill down. Maybe I'm content. Maybe at this level I can solve a problem. Maybe at this level I know, okay, if I want to underline, put a final line, maybe saying this is how many records there are in this table. I've put a final line under the table. I put in another functional unit here. Don't have to change any unit. I just thread in another functional unit. Maybe that's enough for me. But if I want to drill down, well, there's a lot of operations here I can drill down into. Don't want to linger on them. Somewhere there before, some I refactored. But the point I want to make is that this code is object-oriented because it's passing messages around without using MSMQ. Just a plain flow of data. And I bet you can reverse engineer, so to speak, the design of this. You can draw little bubble data flow diagrams by looking at this code. Okay, well, that's just the first step. That's just a functional decomposition. Now I want to go up or go to the orthogonal dimension of containers and refactor to classes. See? What we have here is now I have a format consisting of those 2 methods. Oh, no, let me enlarge this. It's 2 methods. First I'm parsing the data, then I'm formatting the data. 2 steps. And both functions, both responsibilities are delivered by separate classes. There's a CSV parser class doing this parsing stuff, which consists of splitting those lines in some way, and that's just splitting up the whole text into lines, and they're splitting the lines into those fields, record fields. This obviously is what kind of class? This is operation or integration? Well, that's an operational class, right? And then there we have the, what else? There is the table formatter. I look at the table formatter. What kind of class is this? There's an integration class, right? It's focused on integrating. It's easy to read. Maybe it's not so easy to test because it's depending on another class, but it's easy to read. Very nice. And there's the table formatter operations class. This is where I put all those operations. Go away, hide there. But this one is easy to test. I can access every method here and put a unit test on that method. And if each and every method passes those unit tests, well then, I think I can conclude that this one here will be green too. It's depending on those operations. If they are all green, then I guess format header, underline, format body, and assemble those will work like a charm. What else did I do? Introduce CS3. Okay, so that's two of those like levels or aspects of our functional hierarchy. That's operations. I refactored first to operations and integration functions. Now I refactored to operation and integration classes. And see, I didn't think up classes before. You might have started this problem, solving this problem by thinking hard about, oh, which classes should I have there? Oh, what's the functionality of those classes? Oh, let's get out the index cards and play some CRC card game. Oh, yes. And I'm doing it the other way around. That's what messaging to me means. I'm starting from the functions. I'm starting from what has to be done, not which classes do I need. What has to be done? And once I know what has to be done, I've solved the problem. And then, if I like, I can switch the dimension and think about classes, because classes are just containers. Classes are not holy. Classes are just a tool. They are containers to encapsulate stuff. Well, according to which, like, I don't know, aspect should they encapsulate stuff? How do I know? Because I look at patterns, and I see three patterns here. I see the pattern of operations. There's stuff that's just doing logic. And I see the pattern of integration. There's stuff that just integrates other stuff. And I see, well, that's the last step, that's the final step, and I see data. That's why I introduced in the final step the CSV record over here. It's simple, yes, okay. But it now makes what happens more clear because it represents a part of the ubiquitous language of this problem. There are records flowing around. Okay, so let the records flow around. Who's actually producing records? I don't know. We can look at the flow and we don't know and we don't need to know. We can look at the flows here. Do we see the records? Yes, they're coming in. They're coming in from here. There's records, but we actually at this point don't know what the type of the records are. We see that here the records are an enumerable, so something like a list of CSV records. I would depict that, of course, in my little flow diagram like this. There's some text flowing in here. That's the CSV text. Then there's some parsing happening and some formatting happening. And here, right between, there is CSV record. Many of them flowing, so it's with a star here. Now my diagram shows more of the ubiquitous language, which is about parsing and formatting and some table operations, and they are working with records too. And if I need to change my record format, it's clear, and the compiler will show me where I need to adapt my code. So that's the implementation of this picture here. We had two operation classes, the CSV parsing and the table formatting operations, two classes containing all those operations, and then we had the top class for integration, we had the table formatter integration class, and we had one data class down here. Why don't I put the CSV parsing not into the record? Wouldn't that be cool? To provide the record with some CSV parsing? I don't think so. I think it's more important the record stays to what it's really about. It's about structure. It's telling me how this data, well, is laid out in memory. And shouldn't be about how today I define parsing some data. Maybe it's this way, tomorrow I define it another way, tomorrow, the day after tomorrow I define it yet in another way. No, parsing is an altogether different aspect from storing data. Maybe tomorrow I don't want to use CSV data anymore, and the record in its format stays the same, but my data source is some fixed length, record style data, whatever, and the parsing looks different. So why should it go together with the data? Okay, so you saw messaging is actually doable. Messaging actually leads to object-oriented programs, meaning we are using object-oriented technology like a language, C# with its feature like classes and interfaces and dependencies, whatnot. You can use all that, especially, of course, cool functions or functionality like delegates and events. And we arrive at object-oriented programming. That's cool. We can do that. And that's more like what Alan Kay thinks, I guess. Because he said, well, C++ is not what I had in mind when I invented object-oriented programming. To me, that means, in summary, you can do messaging, well, at least the way I define it, with almost any language. And nowadays with Java 8, it's also pretty easy to do it with Java. Before that, it was more difficult than with other languages. You can do it with JavaScript and Ruby and Scala and whatnot. And now with Java 2, that's great. And messaging makes for clean code. I hope you agree with me here. What I showed you, the refactored code, refactored to message functions or messaging functions and messaging classes, was easy to read. The rules are very easy. Look at a function and see whether it contains logic. If so, it shouldn't call other functions. If not, great, it's an integration. So refactor to that. The IOSP principle is the first to apply. Then if you arrive at also close to the bottom, close to the operations, and you might want to focus on the POMO principle of mutual oblivion, because then you have to be careful not to leave some if statement in some integration method. That's easy to happen, but be really rigorous about that and push them down. If you push them down, you might need to introduce continuations, but it's still easy to apply rules. If you do this messaging style programming, you are right on the leading edge with reactive programming. You can use those frameworks like RX framework from Microsoft. And messaging is compatible with domain-specific languages and domain-driven design because it's stratified design, almost by definition. And that means you get your own DSLs without special tools, but just by focusing on certain vocabulary, which differs from the level you're working on in this hierarchy, the operation integration hierarchy. And domain-driven design, yes, of course, you can do that. Just because I pulled out the CSV record data doesn't mean I don't have domain classes, right the other way around. I have very focused domain classes. The CSV parser is a domain class. The formatting classes are domain classes. Just because they don't contain any data doesn't mean they are domain classes. Of course they are. And they could store state, but they don't need to. So I'd say it's all in line with what we already learned about object-oriented programming, but in addition, it's also in line with what Alan Kay said. And that I find very promising because, according to my experience, it's much easier to maintain code built according to those principles than just with the regular solid principles. And before I say thank you, let me tell you, if I'm right, I brought with me, yes, 3 copies of my book on those principles here. Usually it's 99 cents at LeanPub, but there's 3 copies here. If you like, come to me, give me a business card, and I'm gonna flood you with my newsletter. I don't have. And yeah, enjoy. Thank you. Of course, yes, questions if you like.
Showed up like mostly the container reset class of just containers to you. And the functional parts or the integration parts went into class and functional parts went into class. So at the end, don't you run in a class hell? Because you have so many classes at the end.
I wouldn't call it class hell. I would call it like class heaven, because classes seem to be very small. And compared to the 10,000 line classes I've seen, they are very small and focused and dedicated and clear responsibility. And I'm not saying you can put like 100 methods into an integration class if you like, so it's larger. If that suits you, you're welcome. But still keep it to the responsibility of integration. Yes, the classes become smaller, but that's good. And they're becoming smaller not by like an arbitrary measure like not more than 500 lines or whatever, but by focusing on the responsibility. Yes, please.
What would you say to someone who would tell you these are just data classes, you don't have no logic, this is not object-oriented programming? I guess the talk is an answer to that. But
well, I would give this talk. So the reason is to decouple. If you put lots of logic and data, well, see the end between logic and data into one class, you get higher coupling. And you overload it with responsibility, which makes for many changes in this part of the code, and those changes will ripple. Of course, changes to the data structure will ripple, but then it's just changes to data structure and not also changes to some functionality. We have to diffuse, as I said, diffuse those dependencies. That's very important. We are suffering from so many heavyweight dependencies. And this, I find, is a pretty easy to understand way.
you still have data in your operation classes.
Do I have data in my operation
Store
classes?
everything through-
No. Operation classes can have state. That's great. I didn't tell you everything about this like view of the object-oriented world. But one aspect is, yes, they can have state. That's why this is not functional programming, as other people are preaching it. This is like a first step in that direction, maybe, but pulling out state is just another big step, and I don't want to require you to do that. So they can have state. That's great, and state is one indicator of which functions to pull together into a class.
So you have your integration folder and your operation folder. Have any advice on how to structure that once your application becomes much bigger?
That's obvious responsibilities, and I put them in those folders. I could have made up another folder saying that's formatting and put the integration and the operations into a formatting folder. Well, I leave that up to you. I don't have any special advice on that. No. Whether you structure it vertically or horizontally, operations, integration, separating them would be a horizontal structure to the project, and then doing it like with the content-wise responsibility would be a vertical. I don't know. Sometimes I'm doing it like that, sometimes some other way around. Okay, first year.
Okay. I think I agree with the opinion over there. I am unsure that what you're describing is really object orientation, and I certainly disagree with Alan Kay's view of history. I think that this is more like a language called CSP, which was specifically dealing with communicating processes, which was put together in 1974. And it was very influential in lots of languages. But the criticism of CSP languages is that they're good at what they do, but what they don't express is changing topologies. Once you've decided what your data flow is, you're stuck with it, and you can't change it at runtime. Now, you've obviously been doing this for a long time. Have you had any experience like that? Have you run up against that?
Okay, what he was saying, this is close to what Tony Hoare came up with, CSP, communicating sequential processes, right? Okay. There was a special language, yes, maybe. I looked at that, like a bit at least, and at other flow-based programming approaches. And what I came up with is at least not forcing this to be some kind of parallel programming thing. You can do that, as you saw, with traditional functions. So, and you're saying what CSP was criticized of was once you have your data flow, it's hard to change. My experience is right the other way around. Because I have the data flow, because I can even visualize my data flow very easily, I can change it easily because it's confined to those integration functions. I could call them like the flow functions, because within them, the data flow is stitched together, wired up. And once you start thinking about changes, yes, we might be inclined to put changes into existing operations, but then it takes some discipline, yes, holding yourself back, and instead always look for how you can put them into the data flow at some other point. And that's really like rethreading the data flow, maybe doing a detour. Instead of going from A to B, you go from A to X and then to B, or maybe in parallel. And I find that very easy compared to, well, what was there before? How I did object
maintenance programming.
Yeah.
What the criticism of CSP was that you couldn't do it at runtime.
No, okay, I'm sorry. Yes, you couldn't do that at runtime. Well, I haven't encountered a problem where I want to do that at runtime, the rewiring. If I foresee alternative routes through a flow, a larger flow, well, then I have to put them in there, the alternative routes. I can think about some dynamic rewiring, and I even built a runtime engine for that with a true DSL, which contains just the wire-up code, and I only code the operations as true C# statements. With that runtime, I could do some dynamic rewiring. I could even throttle the execution, say, okay, not just pass it along as it comes, but wait. So I could watch what's happening in real time, because all messages get passed every second. And I could dynamically do this over there in parallel or sequentially in different sequential orders. But I haven't really found much application for that. So, okay, I'm sorry. Over there was.
Where would you put the logic that if parsing the CSV file fails, you should not do the formatting? In integration?
Okay, where would I put the logic if something failed? There's different ways to do that. If it's a true exception, so you don't expect this to happen, but it happens anyways, you can actually put parentheses, functional parentheses in the flow. I could draw it. I wouldn't do it now for all. I can draw it for you if you like. That's one way. The other way is think about whether this is truly exceptional or whether it's like an edge case. It's going to happen, not very often, but it's a true case. Then you have a second output. And let some error message, some signal flow out like from the CSV parser and do some whatever, compensation.
Yeah, this might be an obvious question, but I guess you can implement this fully with Java 7.
With Java 7 you can do that, but it's like more cumbersome. Yeah, you have to do those, what's it called, like anonymous interface implementations. Looks a bit ugly. Yeah, you can do the overall idea. Sometimes maybe you would say, okay, I do it a little bit dirty, not so clean with an integration that contains an if, because once you go down, push the ifs down into the operations, you arrive at continuation parsing style. Well, that's not so easy to do. So maybe you want to leave it up there and just stick with the SLA principle, single level of abstraction. That could do. But then, yeah, so wait for Java 8, I guess. More questions?
For streams, what do you use in practice? Observables or any?
I mostly, when I'm using C#, I'm using events and continuations, that's it. And you can think about what kind of data to transport. Is it just like an integer, a stream of integers? How do you finish a stream of integers? That's the point. So maybe it's a -1. The value after the last value is a -1, then the stream is finished. Okay, you use strings, you pass a null, whatever. So you have to think about the end of stream signal. Or you introduce a special like stream element where you can ask, are you the last element? Are you signifying the end of stream? You could do that.
With Rx, that will be built in.
Yeah, with Rx, but then you have the 3 outputs. No? On error, on end, whatever, and on next. You can use Rx, and that's the same thinking, of course. Yeah. So I'm not talking specific technology here, but paradigm, thinking, a thinking tool. And to bring back this, what Alan Kay said at the beginning, back into object orientation, alongside whatever was there before, like encapsulation, inheritance, and so on. And one effect of this is I haven't used, damn, I want to show you something. I haven't used the regular mocking frameworks. I haven't used them in a long time. There's much less need for mocking frameworks because those operations are so independent of each other. And the integrations you hardly need to test because they're so simple. Okay, thank you then. You want Okay, good morning, everybody. Let me start right on time. Somebody will be late anyways. My name is Ralf Westphal. I'm from Germany, and I'm here to entertain you with a peculiar view of object orientation. But first, let me note that it's quite astounding to me that so many people actually want to sit in the front row here. Because you know the usual speaker habit is to pick someone from the front row and let them perform something on stage. Like, you sir, do you want to do a little software design for us here using the OOID method? No. Okay, no. Don't be afraid, I won't do that today. But I want to ask a question up front. What's for you the most important aspect of object orientation? How would you describe it in a bullet point list of attributes? What's object orientation to you? Anybody? Just fire out the words. Encapsulation, great. Maintainability, great. Pardon? Reusability, okay, right on. Something else? Nothing? Come on. Huh? Inheritance, right. And finally, responsibilities, like single responsibilities of objects, classes, okay.
Structured approach?
Structured approach.
Structured approach.
I thought we did that in the 80s. But then, okay, yes. And finally, come on. Yes, okay. That's it? Cool, very cool. So let me introduce this gentleman to you. You know who that is? Anyone? So those organs are working together, of course. Where's the dependency injection there? I only see blood flowing. And then something happens with the blood within the lungs. There's an oxygen CO2 exchange. So where's the dependency injection? I don't see it. Where's the dependence on abstractions instead of concrete services? So who is servicing whom here? Who is servicing whom here? Or, final picture here, since I'm from Germany and we invented this. No, just kidding. Where's the dependency injection here? Where's the inversion of control here? Or is this more like cells? Is this more like message passing? I'd say so. See, for me, message passing, let's go back to the cells here. Message passing means, okay, there's a message. Haha, of course. The acetylcholine. And the guys who are like working on this message, one is the producer here, this nerve cell, and one is the consumer, the muscle cell in this picture. Those guys don't know each other. That's the point. Message passing is about two parties agreeing on a message contract, yes, on some kind of messages they understand and they can produce, but those parties don't know each other. That's the same here. That's the same here. And so I come to my first principle of messaging. That's the principle of mutual oblivion. Messaging is when there's a messages. Who's doing that? Okay, that's not even 10%. And may I ask you what your definition of message passing is?
So I'd say we use two definitions. So we use anhand as a messaging system to communicate between different systems. And we also use an event-based model within an application to notify parts of the application that things have happened.
Okay, thank you. Very interesting. I asked him for the definition of message passing, and he named a couple of technologies. Is that the definition of message passing? Not really. So what's the definition of message passing? Let's turn to Wikipedia again, and it says something like message passing is a way of invoking behavior through some intermediary service or infrastructure. MSMQ. Right, that's an intermediate service or infrastructure. Rather than directly invoking a process, subroutine, or function. So there's some indirection, it seems, necessary for message passing. At least to this, according to this definition. By name as in conventional program, and so on, so on, so on. So the regular method call on an object is not message passing, according to this definition at least. So where's message passing in our daily routine of object-oriented programming? I'd say it's absent. This is deplorable. Alan Kay says, wow, messaging is the big idea, and it's missing. This is, the big idea is messaging is his answer to a question by some interviewer who asked him what's lacking in today's object-oriented programming. So it's missing. I think this could be at least one of the reasons why our object-oriented programs look like they look. They are hard to maintain. It's probably seen him before. No, he's not at the conference. That's Alan Kay. That's actually the guy who invented object orientation. He did that like in the 70s, I guess. And see, that's what he thought was object orientation was to him. Objects being things like biological cells communicating using messages. So did he use the term inheritance? No. Did he use the term polymorphism? No. Encapsulation? Maybe that's hidden behind using messages. Did he use the term reuse? No. Maybe that was of concern to him, but he didn't say so. That's object orientation. Okay, that's what this guy said at least. And now look at the usual definition of object orientation. Let's like Wikipedia page. And you see it's object-oriented programming, and it lists a couple of attributes here. Like, oh, there's classes and instances and abstraction and polymorphism and encapsulation, see there. Whatever. Cool, inheritance, it's all there. And where's messaging? Is messaging there too? It is, indeed, just one of like 10 bullet points. It says message passing. So the next question is, do you know what message passing is? If it's so important, if it's at the root of object orientation, if it's the foundation of object orientation, the most important term of object orientation, because that's what the father of object orientation said. So what does message passing mean? Do you do that in your daily object-oriented practice, message passing? Do you let objects communicate using bound fields as heaps of legacy code you have a hard time to change whenever there are new requirements? Okay, so what can we do? What is messaging? Let's go back to Alan Kay's original idea. See, that's two biological cells. That's a nerve cell and that's a muscle cell. And he had in mind that objects would communicate like biological cells using messages. So where's the message in this picture? It's here. It's the acetylcholine flowing from this nerve cell to the muscle cell. So whenever the nerve cell is like working, it's outputting acetylcholine. This acetylcholine jumps over this gap here, synaptic gap, I guess, to the muscle cell and then makes the muscle cell working. So my question here now is, if object orientation is like those cells communicating, and we are doing object orientation today, then where is there dependency injection in this picture? Because it seems the foundation to today's object-oriented practice. Wherever there are two objects, we're thinking about making them dependent in some way, and then making them not dependent on the actual implementations, but on abstractions, and then the actual implementations get injected at runtime into the caller. Okay, so where's dependency injection in this picture here? Strange, right? It's not there. Or look at this. It's like on the higher level. It's organs.